Hello students, I am Dr. Gajendra Purohit and you are watching my YouTube channel where I upload videos for engineering, mathematics and B.Sc. Today I am teaching discrete mathematics in this video and I will teach you what is partial order relation and total order relation. We also call it POSET and TOSET. We are going to discuss the relation between partial order set and total order set. I have uploaded many videos on discrete mathematics. You can watch them on IIT-JAM as well. You can find the links in the description. To understand this concept, we need to have an idea of the relation between these two first. And for that, we studied that to have an equivalence relation, it needs to satisfy three conditions. First one is reflexive, second is symmetric, and third is transitive. Now we will talk about what a partial order relation is. And it's nothing different from the previous one, just a little change in the definition. If the relation that we have is equivalence, then the second condition there will be symmetric. By any chance, if the condition of being symmetric is not satisfied and it is anti-symmetric, it is reflexive and transitive but becomes anti-symmetric instead of becoming symmetric. So that set or that relation is called partial order relation. Let's take an example. We have a set of 1, 2, 3 and it defines a relation as in 1 with 1, 2 with 2, 3 with 3, 1 with 2, 2 with 3 and 1 with 3 as well. Now we'll check if it's reflexive or not. Being reflexive means that 1 should map with 1, 2 should map with 2, 3 should map with 3 and as you can see, it does follow the order. Now let's check the symmetric. In the symmetry, if 1 is mapping with 2, 2 should also map with 1 as well. If 2 is mapping with 3, then 3 should also map with 2. If 1 is 3, then 3 should also be 1. I've uploaded related videos on the IIT-JAM, you can watch it. However, by any chance, we have 1 with 2 but not 2 with 1, 2 with 3 but not 3 with 2, and 1 with 3 but not 3 with 1. Which means that if it is anti-symmetric, right, and it is transitive, already as if there is 1, 2, 2, 3, then it also has 1, 3 in it. So this set is reflexive, it's not symmetric but anti-symmetric and transitive. Hence this relation becomes a partial order relation. That's how we need to understand it. Let's take one more example. In the set of real numbers, the relation of less than or equal is partial order relation. So this is what we have as partial order relation. This means that the relation less than equal should be reflexive and transitive but not symmetric. And if it is symmetric, then in that case A will be equal to B, right? This is what we need to pay attention to. If we have A, B belongs to R, B, A belongs to R, then A will be 100% equal to B, right? This again is an important thing. Now let's talk about reflexive. Reflexive means A should belong to R, and if a value is large or small in the comparison of itself, then it's already reflexive, right? Next is symmetric. As I've already told you, A less than equal to B and B is less than equal to A. If it happens this way, then A and B belong to R and B and A also belong to R. That's how it can be symmetric. If by chance, if it is not symmetric, and that will happen when A gets equal to B, then it will be anti-symmetric. As you can see on the board, as in the relation set, you can take this as an example that 2 belongs to R and again 2 belongs to R. Then 2 is getting equal to 2, right? If you do this set back and forth, then it will be symmetric. Then we have 3 which can be symmetric, but this other half part cannot be symmetric. If the values in the bracket are different, then it won't be equal to R, as in we have 1, 2, but it will not become 2, 1. So when we have A, B belongs to R and B, A belongs to R, then A, B will always be equal. And that will make it anti-symmetric. This is what we have here, that A is less than equal to B, B is less than equal to A, and then A will be 100% equal to B. This means that this relation is not symmetric but anti-symmetric. Let's move on to transitive now. As per the transitive, we know that if A, B is an R and B, C is an R, then A, C should be an R as well. This means that if A is less than equal to B, B is less than equal to C, then it means that A is smaller than B, B is smaller than C. Then the probability of getting A smaller than C is 100%, which will make A, C and R. That is how the relation here will become transitive. Now as you can see, the relation of less than equal within the real number is reflexive, anti-symmetric and transitive. Hence this is a partial order relation. So this is very important. Let's move ahead. Next we will talk about a partial order set, or we'll call it a POSET. So any set that satisfies the three conditions, that is reflexive, antisymmetric and transitive, that set is called POSET, or we call it a partial order set. That is what is written here, right? As I told you that the set of real numbers is less than or equal to is a partial order relation, so that real number for this will be POSET, right? So this is very important, right? So if we look at the definition of POSET, which is a set A with a partial order relation R is called POSET. And as I told you earlier, the real number when it is less than equal to, then it will be POSET. So how will we write it? As we know, this is on the board. R is a real number and this was our operation. The definition of group is, if G is there with plus operation, it satisfies all four properties, then it is a group, right? Getting my point? So here also, if this set satisfies three conditions, the first condition is reflexive, then second is antisymmetry, and third is transitive. If this real number is satisfied on this operation, then this set is called POSET, and this is what you need to understand here. Now we will talk about total order relation. Total order relation means that every element should be related to another element. But I want to tell you that for total order relation, having a partial order relation is very important. If it is a POSET, then only we will discuss TOSET. It means if there is a partial order relation, then only we will talk about total order relation. This is very important. So partial order relation R in a set A is called a total order relation if every element of A, B belongs to A, such that either A is related to B or B is related to A if we have A is equal to B. That simply means that elements have to relate somewhere here. If it relates, then we'll have a total order relation. We will try to understand it with an example. We will write TOSET as a TOSET. A set with total order relation is called a TOSET. That means whatever set we have, it will have an operation with it and all the elements connect with each other and that will become TOSET. For example, the set of integers with less than or equal to is a TOSET. So this is what TOSET is. Now let me give you an example for this for better understanding. If we talk about the set of integers, so if I define its relation here, we know how it will be in the set of integers. If I write 1, 2, 3, 4, 5 and it will keep going on, 1, 2, 3, 4 and again. It will keep going on like this. So you see here what is happening. Less than 1 is here. So 1 is less than 1, less than equal to 1. 1 is less than equal to 2. 1 is less than equal to 3. 1 is less than equal to 4. Here we can write 1, 1, then 1, 2 and it will keep going on like this. Same way we'll take 2. So we know that 2 is less than equal to 2. Here we will not take 1. It will start with 2, 2. Then it will be 2, 3 and it continues. Then we will start with 3. Now this will start with 3, 3, 3, 4 and it will continue in manner. This way we will have many relations. Now we have to check if these relations which are written as Z and less than equal to are TOSET or not. For that we will discuss reflexives. As we can see, we have 1, 1, 3, 3, then 4, 4, 5, 5 will come as every element is less than and equal to each other. This what we have is reflexive. Now we will check if it's antisymmetric or not. Here you can see we have 1, 2 but there is no 2, 1 here because 2 is not smaller than 1, so it is antisymmetric. Let's see for transitive. Now if I say 1, 2 is there and it goes to 2, 2, then we know that 1 will go to 2. Let's take this 1 is going to 2, 2 is going to 3, 1 will go to 3, then here 1, 3 can also come. This way we have transitive as well. So this set will be POSET. Now we have done the total order relation. The total order relation means something like this. Let me show you an example. If I say that 1 is 100, is 1 connected to 100? You will say yes sir, because 1 is less than or equal to 100. But you will say no sir, 100 is less than or equal to 1. But in any way it should be one of the two, right? It should be 1, 100 or 100, 1. If any one of those two comes, it works for us. As every element could be connected to any other element in any way. Either it can be connected to A or B or B or A. And if it does, then we will have TOSET. Getting my point? So we know that any element will be smaller or equal to some other element. For instance, if I say, let's take 5 and another one is 7. Now 5 is smaller than 7. So you'll say, sir, you can take 7 and 9 and then 7 is smaller than 9. Now you'll suggest me to take 8 and 3, but then you'll say that 8 is smaller than 3, but 3 is smaller than 8, right? And when this relation happens, then it is TOSET. This means both elements should relate to each other in some way or the other. This is very important. Here is the question now. so that the set A, 1, 2, 3, 4 under the divisibility relation is not a total order. That means we do not have a total order relation with the divisibility rule. Now let's do one thing, don't worry. Let us write the set. I will write here. This is A and A. Here I have 1, 2, 3 and 4. 1, 2, 3 and 4. Now let's see what divides what. 1 divide 1, 1 divide 2, 1 divide 3, 1 divide 4. In its relation we will write 1, 1, 1, 2, 1, 3, 1, 4. Next 2 divides 2 and 2 divides 4, but 2 doesn't divide 3. Here we will have 2, 2, 2, 4, but not 2, 3, as 2 does not divide 3. Now 3 divides 3, so here we'll add 3, 3. Then 4 will be divided by 4, so 4, 4 will come. Now we'll check if it's reflexive or not. To be reflexive, each element has to be linked with the same element. As you can see, 1 is linked with 1, 2 is with 2, 3 is with 3, 4 is with 4, which means that this is reflexive. Let's see if it is antisymmetric or not now. This is antisymmetric because 1 maps with 2, but 2 does not map with 1, so this is not symmetric, but antisymmetric. Now this condition and this is also satisfied now. Now let's check transitive, and here it is transitive as. Here we have 1, 2 and 2, 4. Then we have 1, 4 as well as here we have 1, 3 and 3, 4. So 1, 3 is also there. Ultimately we have the transitive as well here. We have this as reflexive, antisymmetric and transitive as well. Now you'll have this question. What are the other conditions to find TOSET? So for TOSET, every element should connect to any other element. Now here you see there's a very good point, and that neither 3 is related to 4 nor 4 is related to 3. If any one of these relates either way, then it will work for us, but neither 3 is related to 4 nor 4 is related to 3, which means this here will not be TOSET. We can also check it in this way, 2 and 3. But here there are also not forming relation. 2, 3 or 3, 2. If any one of these connects, then it's okay. We have 1, 2, so we don't need 2, 1. It's just that we need one thing to connect with others. As the river should start from somewhere to let the water pass from any way possible. As 1 connected to 2, hence this is important. So this will not be TOSET. It will not be total order relation. So this is very important. So the fourth relation that we have here, we just have said that we won't have a concept of comparability. If 3 is mapping with 4 or among 3, 4 or 4, 3, anyone should map. If neither of the two is present, so it won't be comparable here. Similarly, if it will not be TOSET. We will talk about this in the next question. So look at the next question here. Look at the question number 2. In the set of natural numbers 1, 2, 3 up to infinite, show that the relations are defined as A is related to B, which implies A is equal to B power K, where A and B and K belong to a natural number, is a partial order relation. Now we have to prove that this will be a partial order relation. First we will talk about reflexive. In this A should be in the R. Means A should be in the R, which is equal to A power K. And K is a natural number here. And in the place of the natural number K, if I put 1, then A will be equal to A. This means A belongs to R, so we can consider it as reflexive. We will talk about antisymmetric. The thing about the antisymmetric is, let me show it to you. See, what is the concept of antisymmetry? That if A, B is going to R and B, A is going to R, then we should have equals A and B. If A equals B, then it becomes antisymmetric. If we see this, then it means that A is equal to B to the power of K. And from here, B is equal to A to the power of K, right? So we put the value of B here. Let us rename it to K1 and K2, right? So we can write A is equal to B power K2 power K1. Now here we can write it as A is equal to K1, K2. Now we know that the power is here is 1. So these powers will connect with each other. This means K1, K2 are equal to 1. And K1, K2 are both natural numbers. So which natural number has product 1? So here K1 and K2 will be 1. And if K1 and K2 are 1, it means that A will be equal to B. And if K2 is 1, then B will be equal to A, right? So A will be equal to B. This relation will be antisymmetric. So we can understand it very easily. Next, we will talk about transitive. What is transitive? If we have A, B belongs to R and B, C belongs to R, then it implies that A, C should belong to R. If we take this, then A is equal to B power K1 and here B is equal to C power K2. Now we will B replace with C. Here I can write A is equal to C power K2 and K1. Then it will be A equal to C power K2 K1. And now we know that we have two natural numbers. K1 and K2 are two natural numbers. Then the product of it will be a natural number. Then I'll write it as a big K. Then A comma C will also belong to R, as we can write it in the position of power. Here A will relate to C, then A and C will belong to R. So this property here will be transitive. Now question will be raised here. Okay sir, we understand that this is partial order relation, but can we find out if we have a total order relation? So in a total order relation, what happens is that every natural numbers element shall be connected or comparable with every natural numbers element. Now I would like to tell you, for example, I take two elements, 2 and 4. We have to check if 2 and 4 are related to each other or not. Now we know that 4 is the square of 2 and that we take into the power of some natural number, which means that 2, 4 will go to R, right? But if I ask you to consider 2, 3, so what shall be the power of 2 so that it can become equal to 3? So such natural number doesn't exist, where 3 is equal to 2 power k, right? So neither 2 relates to 3 here, nor 3 relates to 2. And here every element should be connected to one or the other element. This should connect to either this or that. As such, 3 equals to 2 power k or 2 equals to 3 power k for any k natural number, right? But it's not happening this way. So here, this will be a partial order relation, but not a total order relation. Let's talk about the next question. This question is good as well. Let X be the set of all 2 by 2 real matrices. Matrices that are given here, x1, x2, x3, x4. And Y matrices are y1, y2, y3, y4. And the relation is X less than equal to Y. This implies that the sum of the 4 elements in set X must be less than or equal to the sum of the 4 elements in set Y. Now you have to prove that this relation will not be a partial order relation. Let's see with the help of an example that this less than equal to here is not antisymmetric, right? That if A is less than equal to B, that is X is less than equal to Y is there, then we will be able to prove that X is not equal to Y. So if I compare the elements of these two matrices and show you that the sum of the elements in one matrix is smaller than the sum of the elements in the other matrix, but the matrices themselves are not the same, as if both matrices are the same, then only we will have antisymmetric matrices. The meaning of antisymmetric is, here I am going to take x, y, so x, y belongs to R and y, x belongs to R. Is it clear? This means that x here is equal to y. Is it clear? That's what we are going to show here. If I take x is less than or equal to y, that's what we are going to show here. If I take x is less than or equal to y, then the sum of the 4 elements in x will be either smaller or equal to the sum of the 4 elements in y. If I take y is less than or equal to x, then the sum of these 4 elements will be equal to the sum of these 4 elements, which means the two sums are equal. This one is less than that and this is also less than that, which means these two are equal. Now let's check if we have any matrices where the sum of their elements is equal and the matrices themselves are also equal. There can be such matrices, but not all. It's not the same for all the matrices. You can take any random example. If I take X matrices 1, 2, minus 3, 4, and the sum of all these is 4. Let's take an example from Y matrices 2, 3, 4, minus 5. So the sum of these all 2 is 4. I'm trying to tell you that these two matrices are not equal. Matrices have to be equal, which means X should be equal to Y. But this is not happening here, which means that the relation here will not be antisymmetric. So this equation cannot be a partial order relation. If any of the three properties gets dissatisfied, then it cannot be a partial order relation. Here we have given one more example. You can also check this one out. Let's check out the next question. If we have two relations, A less than Cartesian and B less than equal to, both of these are POSET. So it is a partial order set. Then show that their Cartesian product will be POSET. That's what we have to prove. The relation defined here is A1, B1 is less than equal to A2, B2, which means the first element should be smaller than the first element and the second element should be smaller than the second element. First, we'll prove if it is reflexive or not. We'll take a comma b from here. So we know that a is smaller than a and b is smaller than b. And we know that a is smaller than equal to a and b is smaller than equal to b. Only that means a comma b is less than and equal to a comma b, right? Hence, we will have a reflexive relation. Next is antisymmetric. So if this is smaller than this and that is smaller than this, then it means that both of the elements are equal. Let's see that if A1 is less than equal to A2 and B1 is less than equal to B2, then we have A2 is less than equal to A1 and B2 is less than equal to B1. Now, as per this condition, you can understand here A1 is less than equal to A2 and A2 is less than equal to A1, which means A1 is equal to A2. We'll see these two. B1 is less than equal to B2 and B2 is less than equal to B1. Then it means that B1 is B2. That means both of these elements will be equal. And this is what the definition of antisymmetric is. So this will be antisymmetric. Moving on to transitive, A1 comma B1 is less than equal to A2 comma B2 and A2 comma B2 is less than equal to A3 comma B3. So we will prove that A1 comma B1 is less than equal to A3 comma B3. So if we see the relation, then A1 is less than equal to A2 and B1 is less than equal to B2. Similarly, here A2 is less than equal to A3 and B2 is less than equal to B3. We'll just take these two together and say that if A1 is smaller than A2 and A2 is smaller than A3, then A1 will be smaller than A3. Similarly, if B1 is smaller than B2 and B2 is smaller than B3, then B1 will be smaller than B3, which means we will get this. That means A1 comma B1 is less than equal to A3 comma B3. Thank you for watching. Please leave your feedback in the comments below. In the last video, you will find the entire playlist for discrete mathematics. I will also be uploading short tricks, combining tips for modern algebra and more, so stay tuned. Don't forget to subscribe to my new channel. Thank you and goodbye.